Well, hi, welcome back. We're starting the unit called thermal energy now, which is going to be a nice connection to some things that we've already studied. So this whole semester we've kind of had this theme of different forms of energy. So this is just one of those forms, thermal energy, and it came up in the unit on mechanical energy because we talked about how thermal energy can be one of those sort of wasted forms of energy. You know, when we have a lot of friction and things heat up, a lot of times that energy is not being put to very good use. So, we talk about roller coasters and how they can generate some thermal energy instead of the more useful mechanical energy just by virtue of the friction between the wheels of the car and the track, for example. This also connects to something from the first semester when we were studying the states of matter. Talked about some of the differences between solids, liquids, and gases had to do with the energy of the particles. And that, although we didn't name it at the time, we could call thermal energy. So the first thing we're going to do in this section is just get used to some of the terminology that we use when we talk about it. And some of this terminology are things that students often confuse with one another. So there are two here on the opening page. The difference between temperature and thermal energy. They're actually related to each other, but they're not the same thing. So the more familiar term that you use is temperature, and temperature is just a measure that we use, and we measure it in things like degrees. In science class it would be degrees Celsius. In everyday usage we probably use Fahrenheit, but that's related to the average kinetic energy. I'll use our abbreviation that we've been using. The average kinetic energy of the particles in an object. And the important word here, I think you know what kinetic energy is. It has to do with how much motion the particles have. But we're talking about an average here. So if we have a lot of particles and they have a lot of energy, that doesn't necessarily mean that they have a high temperature. It just depends on how many you have. But thermal energy, the big difference there is it's a total energy. So it's like we add up all of the energies of all of the particles. So we'll talk a little bit more about that in a second. But it's also not only the kinetic energy, but these particles also have a potential energy. And it's not the gravitational potential energy. We're not talking about taking the particles and lifting them up high. We're talking about how the particles are interacting with each other, usually how close they are to each other. And so this actually has to do with, or is related to, the state of matter. That means, is it a solid, a liquid, or a gas? Okay, so that's what we're referring to there. And then, of course, the kinetic energy has to do, as I said before, with the motion of the particles. But again, the key word here is total. So we can have a lot of total energy and not have a very high temperature. And so we'll talk about that when we get down to these examples in a minute. So there's three factors that will determine how much thermal energy. One, because we're totaling up all the energy of all the particles, it's going to have to do with the number of particles that we have. So if you have more particles, you're just going to add up more and more thermal energy. The other has to do with the temperature, because if you have a different temperature, that means your kinetic energy will be different. And then the third factor, as I was just describing, has to do with the state of matter. So those states like gases are more energetic than a state like a liquid. And a liquid is more energetic than a state of solid. So all three of those kind of play in together. So let's look at some examples here of maybe comparing how much energy these different samples have. So if we have 500 grams of solid gold, boy, wouldn't that be nice? We'd be rich. 500 grams of solid gold at 30 degrees Celsius versus 200 grams of solid gold at 30 degrees Celsius. Notice they're both in the same state. They both have the same temperature. The only difference is we have 500 grams here, which means there must be more particles than in 200 grams. So that one has more thermal energy, even though it has the same temperature. You see how it makes a difference because of the total number for all the particles. Having more particles means we're going to have more thermal energy. What about 100 grams of solid gold at 30 versus 100 grams of solid gold at 50? Now we have the same number of particles, we have the same state of matter, but because this is at a higher temperature, that means the average kinetic energy is higher, and so that will have a higher total thermal energy. And then this last one, now water can be at 100 degrees as either a liquid or as a gas. We call that steam. So we can have 200 grams of liquid water at 100 or 200 grams of steam. That means gas water at 100. And which of those is going to have more thermal energy? Well, we've got the same number of particles because it's the same number of grams. We've got the same temperature, so that means the kinetic energy is no different. But because the state is a higher energy state here, that means the particles will possess more potential energy. And so that is actually a greater thermal energy. You may know this from your experience with cooking. I don't know if you've learned this or not, but steam is actually much more dangerous than boiling water. You can get burned so much more easily because that steam holds so much more thermal energy that it can do a lot more damage to your skin if it gets on you. Okay, so let's look at this question. I say it is not always true that a liquid at room temperature will have more thermal energy than a liquid from the fridge. I think if you ask 100 people on the street, all right, which of these has more energy? This liquid that's been on the counter or the liquid that comes out of the fridge? They would probably say, oh, the one on the counter, because it's at a higher temperature. But there is a situation where the liquid that comes out of the fridge would have a greater thermal energy. And that is a large amount of liquid from the fridge. Suppose you have a whole gallon of water versus a tiny puddle at room temperature. You see the difference there? It's because there's so many more particles, and each of those particles, although on average they have less energy, when we total them up, there's just so many more of them that they add up to be a greater thermal energy. Okay? Some comparisons that I like to use, just a way to kind of make sense of that comparison there, is if we ask the question, well, which is greater, the age of all the teachers in the classroom or the age of all the students in the classroom? Well, I'm certainly a greater average age because, you know, being as old as I am, I'm older than any of the students. But because there's so many more students than there are teachers in my classroom, that if we add up all their ages, they're going to be way, way bigger than I would be by myself. So there's a difference between the average age being higher versus the total age being higher. Okay, let's look at the next page here. Thermal expansion. That might be something that you've heard of before. It's actually a really important property of pretty much everything. Not everything expands in the same way, but I want to use what you know about kinetic energy to explain why most things will expand when they get warmer. So I'll say most, not all. Most objects expand as they get warmer, and that's, again, what we call thermal expansion. Because, here's the why part, the particles have more kinetic energy. Remember, the temperature, or how warm something is related to how much kinetic energy its particles have. So when it's warmer, there is more kinetic energy, which means more motion and more collisions between them, making them take up more space. You can always pause this if I continue on and you're still writing. So one of the key ideas I want you to see here, it is not the particles themselves that are getting bigger. We don't have molecules that suddenly grow in size. It's the space between the particles that is so much greater. And it's a little bit like, gosh, the energy in a kindergarten room versus maybe a typical classroom in high school. So you got a whole lot more collisions and energy going on in that kindergarten classroom, and they just take up so much more space. In a typical high school classroom, maybe you've got 25 students and they're all nicely sitting in their desk in 5 by 5 rows, and you could squeeze them all into a much smaller space. But the kindergarten classroom going crazy. So it's not that the individual size of the particles expands. It is just that the space between them is bigger because there's so many more collisions and so much more energy, and they just kind of push out away from each other. Okay, let's talk about this concept. Two different materials absorb the same amount of thermal energy. They don't always change their temperature the same amount. Example here, you could put two different objects over a fire, and one of them will get much warmer than the other. Now, they're both going to get warmer, but not by the same amount. And it's because every material has this property known as, we call it specific heat. Specific heat. So specific heat describes this. It's the amount of energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? Every material has a certain amount of heat it's going to take to warm it up 1 degree Celsius, and that's for 1 gram. Obviously, if we have more grams, we're going to need more heat because each of the particles has to have more energy for it to raise its temperature. So let's look at this example here, and I described it in words, and I've also shown you a little diagram that I think is really helpful. So if we have a 20-gram block of iron and a 20-gram block of silver, that means they have the same mass, the same number of grams, but silver atoms are twice as heavy as iron atoms. If we go back to the periodic table, remember that from earlier in the year, we would find that a silver atom is about twice the mass of an iron atom. So to have 20 grams of both means we need twice as many iron atoms. Each one is half the mass of this. So these two, even though maybe it doesn't look like they would be the same mass, because these suckers are so much heavier, there's actually 20 grams in each of them. So if both blocks absorb the same amount of thermal energy, so suppose we put them in a pan, we put them over a fire, and we let them absorb the same amount of energy, can you see that they will not raise their temperature the same amount? Okay? Because there's fewer of these silver atoms. All right? That means they each get about twice as much energy as one of these iron atoms is going to get, because the iron atoms have to share that energy with twice as many particles. Okay? So which metal is going to raise its temperature more? Well, it's going to be the silver. Okay? Fewer particles. It's kind of like if you had, a dozen pizzas, and you had to split it among fewer people. Then each person is going to get more pieces of pizza. Here it is this way with thermal energy. Each of the silver atoms gets a greater share of the thermal energy than the iron atoms would. Okay. So which metal has the higher specific heat? Let's go back up here. The energy required to raise the temperature of 1 gram by 1 degrees Celsius. Okay? So now, if we imagine we have just 1 gram of each of these, again, we have twice as many iron atoms as we have silver atoms in 1 gram. And so it's going to take twice as much energy to raise the temperature of iron as it is to raise the temperature of silver by that same 1 degree. So iron. And we would find it has roughly twice the specific heat value as what silver has. All right? So there's a concept, and I can ask you different questions different ways here, and I'll do that in the practice that we have. So go back to this, keep your notes nearby, and that's something you really have to think through.